complicates. All right. Hey, real fast, I'm going to do modern. We're going to do actually modern in two parts. So this will be our modern, really quick, brief review of the whole unit. The first part we're going to talk about is this idea that, hey, light, okay, sometimes acts like a wave, sometimes it acts like a particle. It's really this wave particle that's called a photon. Okay, if you remember in this unit, the idea Max Planck was he had to figure out what is the ideal temperature, and if light was really just a wave, when you heat something up, then you should get all of the frequencies of light at a lower temperature, just less of them, a smaller amplitude. But in fact, what happens is as you heat something up, you get red first. And the reason why you get red first, the lowest temperature it is going to be the lowest energy, and red has the lowest frequency. Okay, but this is Max Planck's equation here, and then just remember Planck's constant is h, and this is on your formula sheet, but just look it up. 6.63 times 10 to the minus 34, and this would be joules, joule times second, or it's 4.14 times 10 to the minus 15th electron volt seconds. So remember, electron volts and joules are really just testing the same. It's just different units for the same thing. This is a really small unit. This is a much bigger unit. Okay, but Max Planck's thing, hopefully that should make sense. We did the photoelectric effect with this. So again, the key to doing physics is being able to draw a picture that represents it. So the photoelectric effect was essentially this. You had a photon of light and hitting a metal, and on your metal you have some electrons. Well, if this photon has enough energy, it can knock an electron off. But remember, those electrons are held onto the metal by a certain amount of energy called the work function. So if we were to write our energy equation from this, it would look like this. Hey, I start with light energy. I have to overcome the work function, and then whatever I'm left with is your kinetic energy. Okay, on your formula sheet, it's written this way. Okay, we did a lab with that where we actually did this. Where we had this was hooked up to a battery, so that hey, if I have a photon hitting it, the electron went and it came back this way. And then the only difference there was from here to here was electrical energy, which was Q times V is electrical energy, and that was equal to the kinetic energy that I started with, but then you had the same deal. Okay, remember this graph was super important, or if we graph kinetic energy and frequency, but it should be easy to remember and understand if you think y equals mx plus b. Oh, well, it was a linear graph, and then what does the slope tell you? Oh yeah, it tells you that. What does the y-intercept tell you? Oh yeah, it tells you that. Okay, remember in this class it's super important to, when you guys are doing graphs, put it, if it's linear, do y equals mx plus b, and then solve for stuff. Okay, but that was photoelectric effect. Remember, it did prove that light behaved like a particle because it depends on how much energy your photons have. You could shine really bright light, which would be really bright light, would be lots of photons. But if they don't have enough energy to overcome the work function, nothing happens. No electrons get knocked off. This was the basis behind photocells. So there you go. Okay. From there, we kind of led into, this idea of of this energy diagram idea where we said if this is n equals 1, this is n equals 2, n equals 3, n equals 4, and then you have n equals infinity. And just remember, a lot of times it was like, hey, this is negative 10 electron volts. Maybe this is negative 6 electron volts. This is negative 4 electron volts. This is negative 3 electron volts, and so on. A couple of key things to remember. This represents the different orbitals for the electron. So it should make sense that this gap is the biggest because that's when the electron is closest to the nucleus. So it's going to be hardest to move it away, where the gaps out here are going to be smaller because it's easier for it to move away. Remember, okay, that we had, actually, we didn't talk about the Compton effect or the Bruy wavelength, but just remember that this is 2 times the Bruy wavelength. I'll do Bruy wavelength in a minute, but that would be 2 times the Bruy wavelength. This would be 3 times the Bruy wavelength, and 4 times, and so on with that. But just remember, if it's like, hey, if I start here and I'm going to absorb a photon, well, that could cause the electron to leave the atom. That would, yeah, I'm absorbing a 10 eV photon, and then you could use this equation and then this equation to do things like find the wavelength and stuff. If I went to here, that would be absorbing a 4 eV photon. If I went to here, that would be absorbing a 6 one. Let's say I go to here, so I absorb the 6, and then I fall to here, then I would release a 2. I would give off, emit a 2 eV photon, and then I would give off a 4. But those type of problems, we did this a lot, so make sure that you guys go back and review this. But it's in essence, it's all about this picture, and then deciding, hey, I am starting here if the problem says that, and tell me all the different photons that you could emit. Well, I could go to there, I could go to there, and then there. I could go to there, and then there. I could go here, and then here. So, and then you could find all the different photons that you could emit. So it's picture, and then use this. Remember, this is the change in energy. Okay? So it's, if I'm going from here to here, the change would be 1 EV. Okay, and then I would have to use this H if I'm doing it in EVs. Okay? All right, let's talk about de Bruy wavelength and Compton effect, because that was the other stuff that talked about light is a particle. That if I have, okay, if you have an electron here and you have a photon coming along, that photon can actually cause a collision, which means, hey, that photon, maybe it is going to reflect back going this way, and my electron's going to go this way, or whatever. Now, you'll notice I drew it with a longer wavelength. Why? Because it gave some of its energy to the electron. And Compton did this. If you think momentum is m times v, and E equals mc squared, well, that means m equals E over c squared. So momentum equals E times c over c squared, which over c, which equals hf this times this, which means momentum is equal to h divided by the wavelength. So the smaller my wavelength, the more momentum I'm going to have, which is why this guy has more momentum. After the collision, it's given some of its momentum to the electron, so it would have a longer wavelength. And then the de Broglie wavelength was this. Remember, Compton said, hey, you know what? If light behaves like a wave, then it should have momentum, and it does. And then de Broglie said, well, you know what? If that there's this idea that, you know, light, which is a wave, acts like a particle, then particles should act like waves. And he rearranged that equation doing some intense algebra, and he came up with this equation. And this is on your formula sheet, just so you're aware. Or again, this is momentum. But this shows that everything has a wavelength. It just so happens that for most objects, that wavelength is so incredibly small that it's not going to diffract or cause interference. You know, if you wanted to find your wavelength, you would take Planck's constant, which is teeny tiny, divided by your momentum. It's going to get even smaller. So your wavelength is going to be so small you can never fit through, you know, a double slit that is like that, or a single slit and diffract or something like that. But electrons can. And in fact, that's what an electron microscope does. It's based on this. So, real fast, the first part of modern, light behaves like a particle. Boom. Photoelectric effect, super important. Photon emission and absorption. And then Compton effect, de Broglie. All right. Bye, kids.